So photonic integration is the ability to realize multiple functions on a chip, like we, for example, know from electrical integration in silicon CMOS technology. In optical integration, we can combine basic building blocks on a chip, this way realizing complex subsystems with high functionality. This is of interest because you're able to produce these kind of chips in large volume with very low cost. And also in many cases, the performance of these kind of chips, integrated function, is much higher, much better than the counterpart in bulk optics. Photonic integration is becoming very important now because the performance and power efficiency of many systems is coming to a limit where much closer interaction between electrical and optical systems is required in order to further improve the performance. And integration enables this co-integration, bringing very close together all the various building blocks at chip level or by hybrid packaging. The applications of photonic circuits today are very clearly in transceivers, optical communication for all kinds of distances. But on the horizon are many more applications, for example, towards LiDAR, for say distance sensing in cars, for example, in neuromorphic computing. That's also a topic we are working on at IBM quite a bit at the moment. Quantum computing, quantum optical links, sensing. There's a whole range of potential additional applications where integrated optics can start to play a role. At IBM, we've been working on silicon photonics at various levels. Already years ago, we've started a project to co-integrate CMOS electronics with silicon photonics. And this technology was in the end also transferred to global foundries, where it's now being applied and commercialized. In addition, at IBM, we have co-integrated new materials on silicon photonics in order to be able to further improve the basic functionality of some of the important building blocks. For example, the co-integration of 3-5 materials for direct integration of lasers or detectors, or also the co-integration of barium titanate as an electro-optic material for ultra-fast modulation, and also for modulation that is purely phase-based, which is very important for high-speed optical communication. So I see future research going in different directions. On the one hand, it's really very important that we continue to improve the performance of current functions, like for example in transceivers. And there the co-integration of new materials, tighter integration of electronics and optics will certainly require much more development and research in order to meet the demands of the future. But then on top of that, new applications can come to play, like for example in sensors, in neuromorphic computing, and in quantum technology.
TechCam.